EIR students, we are now in lecture 26, and as you can see there, we're going to start talking about chapter 15.4, magnetic materials. So this week, in the next 3 lectures, we're going to finish chapter 15, and yeah, what I've seen through the textbook, I can add little value to what the textbook is giving you. So I'm going to go through the theory with you, go through the principles as the textbook does. Here and there something we have to correct in the textbook, and then do a few examples. So hopefully, I'm hoping the next 3 lectures will be with under the 15 minutes. Okay, let's start talking around figure 1518. I need to get myself out of the way here. There we go. Okay, so what we've done in the previous 3 sections is to basically look at a magnetic circuit like this, and we put a coil around it. We calculated the flux density, or perhaps the current needed, or perhaps the number of turns that we needed to set up a certain flux. And all of that has at this stage been with a DC current, or a DC current. What we want to start looking at now, as we're going to move towards transformers in the next lecture, is what happens if we apply an AC current to that coil there instead of just a DC current. Okay, now first thing, if we were to zoom in under a microscope in just that little section, you would see that, well, you'd have to zoom in like really a lot. But basically your iron or any magnetic material consists out of little magnetic domains. We call it domains. And each of those domains effectively consist out of a grouped set of atoms with electrons running around them. And as we mentioned earlier, all magnetic fields are set up by electrical current, even if it is on an atomic level with electrons running around it. So those group of atoms then have their electrons, or the resultant effect of the electrons running around them, creating a magnetic field pointing in a random in a specific direction for that specific domain. But between the domains, they're all pointing in their own directions, which effectively causes a net result of 0 in the magnetic material, unless we apply an external force, our coil with a current, that forces these domains to start looking in one direction. So that would be the same as standing in front of a crowd and telling everybody, okay, look right, look left, and forcing them to look in a direction. Alright, so what happens? Initially we start here at point number 1. Let me move that on a little bit still, where your material or your iron is, there's no magnetism in it. So think of an electromagnet that you were going to build, a piece of iron rod or a nail, and you put a coil around it and a battery. Alright, so initially your nail or your core isn't magnetized. Then we start increasing the current. So you'll see what we've, perhaps the axis first. Hey, flux density on the vertical, H, or our magnetic field intensity on the horizontal. Now I actually wanted to put here a little note here. So remember, H equals Ni divided by L. So that comes from Ampere's law. I don't want, who's going to guess this? Let's make this times New Roman. Thank you. Ni, the number of turns, times current divided by the length, and B, remember, equals phi divided by area. All right, I'm just going to type it in like this. So we control the H by controlling the current. All right, so that we can do. So we increase the current. Let's move this down a little bit. And as we increase it, more and more of these domains start pointing in the same direction. But you'll notice it's not a straight line. So up till now, when we said that B equals mu H, we assumed that mu, that permeability, is constant. It's a linear equation. But your BH curve actually does not have a linear curve. Alright, again, the crowd of people example, if you say softly, everybody look to the left, then a few will look there. But the harder you shout, the more eventually you will get there. But you will always get a few hard-headed ones that deaf ones that just doesn't want to listen. So you really have to put in more and more H, more and more effort to get the flux density going. But eventually, all of your domains, or the vast majority of your domains, will point in the same direction. So at this point up here, at point number 3, it doesn't matter how much extra current you put in, there's just not any more domains left to align in the direction that you want the flux, or that you are pushing the flux. So that's the point of saturation. All right, so no more domains that can point in that direction. So now think of AC current. We've increased our current, and at some point it just won't help putting in more current. Now we're going to reverse, or we're going to switch that current off. So we're going to make H, or that Ni, we're going to make 0. We're going to, on the horizontal axis, come back to this point. But you'll notice here at point number 4 that your flux doesn't go to 0. All right, there's some flux left. We call it residual flux. Residual flux. Now, why is that? After you've got your crowd of people to look everybody to the left, and you say, okay, thank you very much, experiment's over, then everybody's not going to turn back to the way they were. I mean, some people are just too lazy, and they'll just keep on staring and looking in the direction that they've turned. Too much effort to turn back. So some of your domains here are not going to return to their original position. Quite a few of them, and that, well, it depends on the type of material that we're going to use. We will talk about that just now. Some of them will keep on looking in the original direction. So you will have some flux density left. So that's now the equivalent of your nail. You had coils, you connected the battery, you put it there for a while, took the battery off, but now your nail is still a little bit magnetic for a short while. Hey, well, until you start picking stuff up. What happens then? It loses its magnetization. So we can get rid of this magnetization, go to 0.5, either by reversing our current direction. So we put our H, our effort, in the opposite direction until we have enough domains looking in the opposite direction, so that my residual flux density is all gone, no magnetism left. Or if you've got your nail, if you start picking up stuff, eventually some of that energy stored in that magnetic field goes into whatever it is you're picking up, and it loses its magnetism. So that's the other way that you can do it. If we keep on decreasing our current or making it bigger in the opposite direction, AC current, you're going to go to the opposite direction of saturation, opposite side. So now you've told the people, look left, now you're taking them, no, look right, and you get everyone to look right with enough compensation and motivation, and you're saturated in the opposite region. Now your AC current goes back in the opposite, but now you're moving along this S-shaped curve, and that is called our BH curve, or a hysteresis curve, a hysteresis loop, all right, in the BH plane. All right, so that's what the first few bits on page 746 talks about. You can go and read through that section. What we want to look at now, and I'm going to show you a couple of nice pictures on this just later on in later sections. What I want to discuss next, the textbook has the little heading there. Let's just go down. Energy considerations. All right. So they start off with this equation, and I'm going to show you, give you another one here on the screen just now, on how they calculate the energy. The energy, I want to underline this. We want the energy there delivered to the coil is the integral of the power. So what we're calculating here is the energy delivered to the coil. So we know that energy equals, let me just give my little hand back. Energy is VI dt, so power times let's say power multiplied with time. So this is just the surface area, energy. Then they substitute the V with d lambda dt, so that you eventually get n d phi dt times I. So now we are still, and now our integral changes with respect to flux. So we integrate from 0 to phi, but remember, flux, if we go up again, is related to flux density. Okay, So Ni d phi. So we actually, what we're busy doing here is integrating along our b-axis. Okay, and that's what they're doing over here. So the Ni they replace with Ampere's law with HL. D phi becomes A dB because B flux equals B times A. And that then changes our equation that we're actually integrating on the b-axis relative to flux density, a L area times length times our field intensity. But that AL is nothing but the volume of your core. That's your core volume. So what they then do is to divide that energy by the core volume, and then you get capital W subscript V for volume. So this is known as your volumetric energy. Here we go. How do I draw a little blocky here? Let's just go here. The volumetric energy delivered to, let's extend this one. Can I? Yeah, delivered to the coil. All right, so that's the volumetric energy delivered to the coil. But that energy can be broken up in a bit of pieces. So we've got electrical energy coming in. Let's go back to this one. So we've got energy coming in. That's what we calculated. So that integral that we've seen now, or that volumetric energy, is how much energy am I delivering through my coil. But that energy then gets divided into a couple of things, and that they list here as well. Part of this energy is returned to the circuit when H is reduced to 0. Alright, so some of the energy gets pushed back into my source. Secondly, part of it remains stored in the residual field. That B that, oopsie, let's go down. That B that remains there. And then the third part is converted to heat in the process of magnetizing the core. Alright, that we're going to focus on now. And that is called core loss. Now, this is a correction that you need to make. I need you in this next paragraph that we're going to discuss. So we're going to talk about this heat converted in magnetizing the core. Where it says here core loss, where it says core loss over here, let me just see if there's not another spot. No, it's those two points. I need you to replace the core. So let's see if I can do that in this one. It's not going to do it. Okay, so let me do this. That core needs to be replaced with, and let's type there, hysteresis loss over there. I'll move it up just a little bit just now. Alright, so get rid of where it says core loss and write for me there hysteresis loss. Alright, oopsie, bit too long that line there. Let's just make it a little bit shorter. I just want to get rid of the core. Okay, and you'll see just, whoops, just now why. Okay, so why hysteresis loss? Now hysteresis loss, let's go back into that domain picture. As your core, I want to do this. There we go. Okay, there we go. As you shunt your magnetic domains left, right, the whole time as your AC voltage changes, you're basically taking those domains and they are rubbing against each other, right? They're rubbing against each other. Now what happens if you rub your hands together? You get heat, and the same happens in this hysteresis loss. So physically, with those atoms rubbing against each other, because they have to go left, right, some of them turn clockwise, other counterclockwise, either way, you've got a lot of rubbing happening inside of that core. So that causes what we call heat, or what we call hysteresis loss. All right. Now, how do we calculate that loss? The volume, you'll see here figure 15.2 that way, 15.20. The area of the hysteresis loop is the volumetric energy converted to heat per cycle. All right, so our hysteresis loop, hysteresis loss. Okay, so that area over there represents the amount of heat that each cycle, because remember, you're going to start there, go down, and then, oopsie, go, and then go back up. And that happens for each cycle of your AC current. So the area is the volumetric energy. To calculate the power, then you simply have to multiply it by the number of cycles that you do per second. Okay, since it's a fixed amount of energy is converted to heat for each cycle, the power loss due to hysteresis is proportional to frequency. All right, so that's important. I think we can type that in. So P hysteresis, so call it hysteresis, is equals Kf. All right, so it's proportional, that's where the K comes in, to frequency. All right, I can zoom in a little bit there. So hysteresis loss P is proportional K to your frequency. All right, so how do we get rid of this? In motors and generators and transformers, conversion of energy into heat is undesirable. You don't want your motor or your transformer to heat up. So in that case, we choose an alloy that has a very thin BH curve. Okay, and this is where I'm going to go over to, not that's this one. Okay, Shift F5, and then we want to go to screen only. All right. So here's our BH curve again. Yeah, I'm just showing, where's my little thing? All right, the domains, random domains, we bring it up, all of them pointing in one direction. Go back. At this point, they're all pointing in random directions again after you've applied enough reverse effort, and here they're all pointing to the left. So for our transformers and motors, we want to be a very thin BH curve so that the area, sorry, you can't like a C there, is thin. So thin soft iron, if you're going to use a motor or transformer, or a very wide BH curve if you want to use a permanent magnet. You don't want your permanent magnet to lose its magnetism, so you want a lot of effort is required to get rid of the magnetism. Now, this picture in reality, if you were to compare the two BH curves for the tube, that thin soft iron loop compared to the permanent magnet's BH curve will actually just look like a single line. You won't even notice the area there if you were to compare soft iron cores like you get in transformers and machines to what you get in transformer. Right, and then also just your hysteresis loss is proportional to frequency. Okay, let's go back to my PDF. Where is that one? There we go. Okay, that's on that one, and then so that's the one type of loss. Hysteresis loss. Then the other type of loss that we get is eddy current loss. Now, where does that come in? Now, remember, the core that you're using is a magnetic material, like an iron alloy, but it's magnetic. And itself, that core can conduct electricity. So a lot of my final year projects around this time of the year, when they start winding their motors, they forget to put an insulating material in their slots in the rotors. They do the windings, and then the winding insulation cuts through, makes contact with the core material, and it creates a short to the core, and then they have to redo the whole thing. So your core can conduct, and now what you're doing in your core is you're actually creating a changing flux. So you are inducing voltages in your core material through Faraday's law. If you are inducing voltages, those voltages in the core aren't the same everywhere. So you've got a higher voltage here, lower voltage there, high, low, low, high, all around. And what's going to happen? If you've got a potential difference between 2 points, current. You're going to have currents flowing in the core, but according to Lenz's law, that flow of current will try and oppose the change of flux. So you actually get circulating currents. Let's go back to this one. I want to show this slide. There we go. So you actually get circulating currents in your material as the flux changes. Now, how do we get rid of that? So that current then causes I squared R losses, also heat, just like in a normal resistor, I squared R losses. So how we get rid of that, and let's do this bottom left picture first, is we do lamination. So you'll see in transformers, motors, it's always thin sheets of metal And now I need to be able to draw on this. So let me just get a pen, pointer, pen. There we go. Now, the flux, if we look at this coil and you put your hand around it, the flux direction will be, hey, draw, Boetie, in this direction. Okay. So the flux doesn't mind the lamination because it's going through a solid piece of material. But looking from the top, where's my pointer now? There we go. Looking from the top, by breaking up the solid core into thin sheets of metal like you have here, instead of that I squared R losses and that current running through your whole core, you're limiting it into much smaller currents. This one also shows limiting it into much smaller little currents flowing. So your currents become smaller, hence your I squared R losses become smaller. Okay, in a laminated core. Now there are circumstances where you don't want to laminate, and that's this top left picture. So what you have here is a piece of rod that you want to melt. You've got a coil around it. Now that coil is that thick, not because it needs to carry that amount of current, but because you've got water or a coolant running in that coil. And what they then do is to run an extremely high frequency current through this coil. And that high frequency, then the high rate of change. Remember Faraday's law says that the induced voltage equals d lambda dt, n d flux dt. So the higher the rate of change, the higher the induced voltage. The higher the voltage, the higher the currents flowing. And in this specific scenario, eddy currents, because it's effectively V squared over R. I think your textbook actually does give you that equation for the eddy current loss. Yeah, P equals V squared over R. But the voltage is proportional to the rate. In other words, your eddy current loss is proportional to the squared of the frequency. So now we give this a high frequency, it creates massive high eddy currents, massive losses, to the extent that that iron will actually melt. And we call it induction heating or induction melting. So you could go and look at a couple of videos on the web. I've just searched a few of those to see how it happens. And it happens extremely fast, this induction heating. All right, the induction cookers that you get in stoves, I'll get the words confused. Induction stove plates, exactly the same principle. So I've got one of my project students building an induction stove plate. So you have a flat coil, it creates, you put your iron pot or alloy on top of it, creates eddy currents in the pot, and it heats up your pot. In this case, they're just taking it to the extreme in that they're actually melting the metal. All right, which you don't want to do with your pot on the stove. Bad idea. Okay, let's go back to our PDF. Never mind. Where's my PDF? That one. There we go. All right. So here in your textbook, P equals V squared over R. So it's proportional to the square of the frequency, and that they state here on this page. For operation with a given flux density, the voltages induced in the core are proportional to the frequency because of Faraday's law. Therefore, power loss due to the eddy currents increases with the square of the frequency. Okay. Now, this is where the textbook, let me just quickly go to the board to explain this one. We've spoken about hysteresis loss. Hysteresis loss proportional to the frequency. How many times, how fast are you going up and down your BH curve or around your hysteresis loop? Eddy current loss is proportional to frequency squared. So both of them manifest in heat. And that, the combination of the two, is called core loss. All right, so that you will find in all other textbook, machine textbooks, that core loss is divided into hysteresis losses and eddy current loss. So perhaps let's just add the last bit there. Okay, those two components. So in the test and the exam, I'm going to test you on this principle. What does core loss consist of? Hysteresis loss, eddy current loss in your machine. And when we get to induction motors and transformers, actually not next lecture, the lecture after that, we're going to come back to this concept of core losses. All right, so hysteresis, eddy currents combined forms your core loss. All right, not like in the textbook where they equate core loss to hysteresis loss. So hopefully you made that fixed. Okay, let's go back to the textbook. In the next section that we're going to discuss, we are looking at energy stored in a magnetic field. Now they're actually going to follow on from this equation where we ended up with a volumetric energy. Now remember, this equation calculated the surface area of our hysteresis loop. What we're going to do for the next section is to assume that your BH relationship is a linear relationship. And as the textbook explains in this section, you do not want to saturate your core. So we mostly operate our motors, transformers within a linear region of the BH curve. So for the next, we're just going to assume that your BH is still a linear relationship. Okay. Now, if we then, into that equation 1540, and I'll show the whole thing again on the screen, substitute, then you get this volumetric energy B over mu, so we've replaced the H, and you integrate and you get B squared over 2 mu. And that then gives you an equation that if you know your flux density in your circuit, which we calculated in the previous lectures, if you can calculate your flux density in your circuit, you know the permeability of your material, you know the joules per cubic meters. The joules per cubic meters. It's still a small little v there. So if you want to know the actual joules, the actual energy stored in there, then you just need to multiply with the volume of the core. Correct. You need to multiply with the volume of the core. Now, this little part in italics here, notice this equation, the amount of energy, or the energy density we call it, that volumetric energy or the energy density is proportional to the inverse of the permeability. In other words, let me come closer. Okay, I want to keep that in view there. In other words, if I make this mu smaller, what's going to happen to the volumetric energy? It's going to go up. Make mu smaller, volumetric goes up. If I make the mu higher, then obviously the volumetric energy is going to come down. Now think in terms of a core with an air gap. The core material permeability versus air gap permeability. Which one has the lowest permeability? The air gap, by factors of thousands, because the relative permeability of the core can be anything, what do we say, 1,000 to 1,000,000 for some types, but it's thousands. So the permeability of my air gap is thousands times smaller than the core, which means in a magnetic circuit with core and air gap, where is all the energy going to be sitting? In the air gap, right? So all of the energy basically resides in your air gap. And it's for that reason when we analyze magnetic circuits in my ELX third year course, the permeability of air is so much higher, all the energy is stored in the air gap, so most cases we simply just ignore the core material. Alright, so all the energy goes and sits there. I think I'm going to talk through this example, exercise 15.4. Do I want to do it? No, I actually want to do exercise 15.4. So yeah, let's quickly jump to the board again. Exercise 15.14. Exercise 15.14. It reads: consider a coil wound on an iron core for a 60 Hz AC operation. Okay, so F equals 60 Hz. Where are we now? A given applied current, the hysteresis loop of the core material has an area of 40 joules per cubic meters. So what did I call that? Yeah. So the volume core is, the area, the volumetric. Where am I now? Sorry. It's actually WV that they give us. The energy density is 40 joules per cubic meters. And then they give us the core volume. That's where I wanted to write the VC. The core volume is 200 cubic centimeters. Now already cubic meters, cubic centimeters. All right, we're going to fix this just now. They then want the power converted to heat because of hysteresis. So they want P hysteresis, and we know that is, well, P hysteresis is proportional to frequency. Okay, so that we've learned. All right. So what else do we know about power? We also know that power equals the rate at which we consume energy. The rate at which we consume energy. So I need energy and I need a rate. First, let's get the actual energy. So the energy stored in my core is the volumetric energy times the volume of my core. So I've got 40 joules per cubic meters. The 40 times the volume of the core is 200. But what's the problem here? Cubic centimeters, cubic meters. So I need to convert cubic centimeters into cubic meters. So that's going to be times 10 to the minus 6. Okay. Because a centimeter is 10 to the minus 2 meters, you take that to the cube and you get 10 to the minus 6. Okay, and then we get this chalky doesn't want to talk today. 8, are you kidding me? Just a whole 8 millijoules. 8 millijoules. 8 millijoules. Right. So that gives me the energy bit. Now to get the actual P, I need something divided by time, the rate. Now where do I get here something with that's a rate? Well, that's 60 hertz. What's the unit of hertz? 60 times 1 over seconds. All right, hertz is per second. So it's simply going to be WC times your frequency. So it's 8 millijoules times 60 1 over second. So I've got joules per second. So I've got 48, 480 milliwatts. All right, that is how much heat actually gets generated in the core due to hysteresis. So this is not all the heat. Oopsie, let's just put maybe an hysteresis there. So that's not the total core loss. That's only because of hysteresis. We don't know what the eddy current losses in this thing is yet. All right, so that's exercise 1514 that I wanted to go through. Next, I want to go through exercise 1515. So let me just quickly wipe out here. So exercise 1515 reads, a certain iron core has an air gap. All right, so I've just drawn, there's no picture in your textbook, I've just drawn a core. It could have been a donut shaped, I don't know, I just draw a blocky one. Now it's going to be a blocky one, you're going to see just now. And this core has an air gap with an effective area of 2 centimeters by 3 centimeters. Now that little word effective means that the effect of the fringing is already included. So this air gap over here, the air gap area AG is 2 by 3 centimeters squared, and the length of the air gap they give there is 0.5 centimeters. So don't now go and add the 0.5 to the 2 and the 3 and say it's 2.5 times 3.5. Okay, they already give us here the effective air gap area, so you just use the 2 by 3. They don't give the dimensions of the core material because we're going to ignore the core. So you're supposed to add the 0.5 to the core's cross-sectional area dimensions. It's not the core that's 2 by 3, it's the air gap's effective area that's 2 by 3. So the effective area is going to be 6 squared centimeters. The applied MMF is 1,000 ampere turns, so that I've put down here. And the reluctance of the ion is negligible. They don't give us anything of the ion because that's going to be negligible. What we need to find, flux density in the gap and the amount of energy stored in the gap. So if you want to solve a magnetic circuit, you need a circuit diagram. And now I've taken a bit of space there. Okay, but let's draw it here. So we've got our MMF, reluctance of the core, reluctance of the air gap. But this one of the core, did I even draw it in here? No. So let's say our RC is 0. So that they give us. We can assume that's 0. But then we need the RG so that we can calculate the flux, so that we can calculate the flux density in my air gap. All right. So always we start with F equals Ni equals flux times reluctance. Everything is in series. So this R is only going to be, the total area is just Rg because Rc is 0. We know the MMF, it's 1,000. In other words, if I know the MMF, the reluctance I can calculate because I've got the area, I've got the length and permeability of air, we know. So reluctance is not a problem. So from the flux will then give us the flux density, and from the flux density we will get the energy stored in the gap. So that's our route that we need to follow. Get the reluctance, get the flux density, then we can get the energy. Right, so let's start with Rg is the length of the gap divided by mu 0 times the area of the gap. It's 0.5 times 10 to the minus 2 over mu 0, which is 4 pi times 10 to the minus 7. And then AOG is 6 times 10 to the minus 4. And what did I get? I got a reluctance there of, is it going to fit here? 6. Well, how did I write this? 6, 3, 1, 4, 5, 5. And I don't have, this is ampere turns per Weber. All right, ampere turns per Weber. Okay, so now we can go and get the reluctance. So in other words, now we can get flux equals the MMF divided by the reluctance equals 1,000 divided by the 6. Now let's write the whole thing out. 6, 6, 3, 1, 4, 5, 5. And that gave me a flux of 150.8. 150, chalky. 150.8, probably microwebers. Yep. Microwebers. All right. It's a new box of chalk, so it still needs to acclimatize, I suppose. Now I've got the flux. Next, flux density. So this flux now, remember, is the flux flowing everywhere. Air gap, no, everything is in series, so it's the same flux. So B of G then is the total flux divided by the area of that gap. So it's the 150.8 times 10 to the minus 6 divided by, what was the area, is 6 times 10 to the minus 4. So you see here the micros I'm including there, the minus 4 because it needs to be in square meters. All right, and that gives me a flux density of 251.3 millitesla. Okay, that's the one way to get to the flux density, or the one answer. There is a shortcut way that you can use, and that's through Ampere's law. I wonder if I'm going to show you this. Yeah, I'm going to show you. Okay, so this is the one way. Let me just draw a line there. Okay, an alternative way to get to BG is to do the following. And that, remember, in one of the lectures I told you there's actually another equation to the right of this. Through Ampere's law, we know that MMF equals Ni equals HL. All right. Do we have Ni? Yes, it's the 1,000. Do we have the length of my air gap? The 0.5 centimeters. So it's only the H we don't know. So we can say that this equals B, because B equals mu H. So this is going to be B over mu 0 times the length. So from this is going to be the air gap because we're ignoring the core material. From this equation, we can directly get the flux density because we know the length, we've got mu 0. If you were to go and simplify all of these equations, you're going to end up there anyway. There's just a big, very dangerous thing in this equation, and that is, what if you cannot ignore the core material? In this case, we ignored the core reluctance. What happens if you don't ignore it? Then there's going to be two HL terms. There's going to be an HClC for the core. There's going to be HGLG. But that I do with my third years. What I think for you guys, the safest method is to use Ohm's law, flux times reluctance. And yeah, this you can do as a quick method just to test. Okay, but you'll get the same answer there. Right. Then we've got the flux density. Now we need to get the energy. Just want to see how much space did I use here. Okay, I'm going to wipe this just for the sake of space. Okay, so flux density, fine, we've calculated that now as what again? 251.3 millitesla. Okay, energy in the gap is going to be the energy density in the air gap, energy density, volumetric energy, times the volume of my gap, the volume of my air gap. So first I need that WV. So let's just leave some space here for that calculation. So let's get the volumetric energy. That is B squared over 2 mu 0. So in this case, I'm using mu 0 because it's air. That G, that's the air gap volumetric energy, density. We know what that is. It's 251.3 times 10 to the minus 3. This all needs to be squared. Divide by 2 times, let me write it out for a change, 4 pi times 10 to the minus 7. Okay, and that gives me a volumetric energy of 25132.7 joules per cubic meters. Whoa, and you're thinking, well, here comes a big answer. Hey, we've got 25,000 joules, but it's per cubic meter. So now we need to take this massive value and squeeze it in there where I haven't left any space. Yeah, anyway, let's first calculate the area of the gap. So that's AG LG 6 by 0.5 equals 3 cubic centimeters, right? Because that's all in centimeters. So typically in your spreadsheet, where I leave a space for AG, VG, or LG, I always ask that in centimeters, squared centimeters, cubic centimeters. Otherwise the numbers become very small. But now when we're going to move over to calculating the actual energy, remember to convert that into cubic meters. Okay, so substitute these two into my energy equation. Let's redo it here at the bottom. So the energy stored in the gap is the volumetric 25132.7 multiplied, that's in joules per cubic centimeters, and now I need to take this times 3 times 10 to the minus 6. The 10 to the minus 6 takes the cubic centimeters into cubic meters, and I get 75.4 equals 75.4 millijoules. All right, so there's the one answer. There's the other answer. So all of a sudden, not a lot of energy. I started with a big number, ended with a very small number there. Okay, that was exercise 1515. And guess what? That's it for this small little lecture on magnetic materials. So what do I expect from you is the theory bit. know what hysteresis is, know what saturation is, what is hysteresis loss, what is eddy current loss. They combine to form core loss. And with these examples, we actually went and calculated, okay, but what are the losses in the core? So all the energy, flux density, energy stored, hysteresis losses in the core. So what we've done in the exercises here, and yeah, you'll see in the homework problems what you need to do there. That's what I'm going to expect from you. Okay, that's it for lecture 26. Next one, we're going to finally move over to transformers, ideal transformers. You'll see me in the next one. Cheers. Bye-bye.